Okay, so I think we can start now. All attendees are joining, or the others are joining us, but it's a time. So ladies and gentlemen, welcome to our new IDEA StatiCa webinar, which focuses on structural optimization of a precast beam. Just to introduce ourselves, my name is Jan and I'm consultant at IDEA StatiCa, and I'm here with my colleague Orsolia Kartali, product engineer. You can see us at the web camera. So hi.
Hi.
So about the webinar, you can ask questions, use a window on the right side of your screen. Anything which came up to your mind, just write a note, question, anything. We'll try to answer the questions during the webinar, and the rest we will answer after the webinar. So don't hesitate to ask us. We are happy for anything you ask. So let's go to the webinar itself. I'll talk a little bit about the agenda. First, I will tell you something about the project and the company, because today we have a project from our customer, which is always more interesting than just some general project. My colleague Orsolia will tell you something about preliminary design, then optimization of geometry, the first step. Then we will talk about creation of stud and tie models. Next step will be optimization of geometry, and the last one will be the validation and code check using IDEA StatiCa Detail, and the conclusion and comparison of both approaches. So first, about the project and the company, I would like to thank you, our customer company S-projekt Plus from Zlín in Czech Republic, and Mr. Jakub Koníček, who provided us the model information. S-projekt Plus has a wide portfolio of projects, mainly industrial halls, shopping centers, office buildings, schools, everything. It's a mid-size design company in Czech Republic, and they have well-known companies as customers like Skoda Auto, Toyota, Kaufland, Tesco, etc. If you want to see more information about S-projekt, just visit their web page. About the project itself, the main goal of the project was to find lightest precast reinforced beam in an existing structure of industrial hall. The span of the beam is 24 meters, and they were looking for really lightest possible design because it has some implication to the existing structure. So the main goal was to find the lightest option, how the beam can be done. So that's about the project, and now I will pass the word to Orsolia, and she will tell you more about the project itself, and she will go through the application with you. So it's yours, Orsi.
Thank you, Hansa, very much. I will just make sure to share my screen with you. So, something about the preliminary design of this project. The geometry, the cross-section, and the loads. The geometry, the 24-meter span length was given. So the engineer have chosen the depth of the cross-section as 1.6 meters as 1/15 of the span length. The cross-section will be a T-section with the depth 1.6 meters and the width of the flange 0.5 meters, as you see in the picture. Concrete grade will be C40/50 and the reinforcement B500B. As for the structural scheme, we are dealing with a simply supported single span beam, span length 24 meters. The loads that have to be considered are self-weight, permanent load, and variable load. All these loads are line loads on the whole length of the beam. As a first step, the engineer designed the bottom reinforcement using the well-known easy design method described in Eurocode, and he designed 6 longitudinal rebars to the bottom edge of the cross-section with 28 and 25 millimeter diameter, and provided a simple code check if the design was correct in this first step. Then he decided to optimize the geometry, and for this optimization he used hinged ends of the beams. Because the main goal is to achieve a minimal weight of the beam, the hinges were chosen, and also because the bending moments are parabolic, the diagrams of bending moments, we do not need to maintain a constant depth of cross-section all along the beam. We can make advantage of using hinges if we want to minimize the weight. The length of the hinge will be 1/4 of the span length. It is 6 meters, and it was chosen using an iterational method for this shape. One of the consequences of this hinge design is that now our beam has D regions on both ends, these regions of discontinuity, and B region in the middle part. In B regions, we can design and code-check using the basic design methods, but for the regions of discontinuity, we have to use special approaches. The engineer designed these D regions using 2 approaches. Since they are first-time users of the application IDEA StatiCa Detail, they wanted to make sure they can use it confidently, and they compared the 2 design methods, the strut and tie analogy and the compatible stress field method, which is implemented in IDEA StatiCa Detail. And after the design, they compared the results from both these design methods. This is what we will show in this webinar. So he needed to create strut and tie models for the D regions of the beam. How should we create a realistic strut and tie model? The engineer decided to use IDEA StatiCa Detail in this first step of the creation already, because we have a topology optimization design tool implemented in IDEA StatiCa Detail, which can show us the topology of struts and ties in the concrete structures based on the input geometry and the input loads. With the blue color, you can see the regions in tension, and with red colors, the regions in compression, the struts. We see that we have growing angles in the hinge part of the beams, the growing angle of the compressive strut, and we have constant angle, approximately 45 degrees of the compressive strut in the middle part. According to that, he created the first models for strut and tie analogy, as you can see in the pictures, with the growing angles in the hinge part. He created, in fact, not only one strut and tie model, but several models to make sure the design was done correctly, and he analyzed all these models for the load and code-checked the struts and ties and nodes according to this strut and tie method. The final reinforcement based on the strut and tie models looked something like this in the pictures. And then comes the second step of optimization. Because the geometry can be further optimized using openings in the middle part, in the part which was up till now a B region in the beam. Now we can add openings to minimize the self-weight of the beam. But because of that, the whole beam became one D region. The positioning of openings is important, and the engineer positioned the openings according to the strut and tie model. And he also checked the direction of principal stresses in IDEA StatiCa Detail if they correspond with the direction of compressive struts, which were assumed in the strut and tie models, and they compared really well. Now the decision had to be made about the diameter of the openings, and of course he wanted to use the maximal opening size, So he chose 900 millimeter diameter for the openings based on the geometry of the strut and tie models. And then came the validation and code checking using IDEA StatiCa Detail. So let's jump into the application and show how quickly we can model such a beam right in the application, including geometry, loads, and some reinforcement. So I will launch IDEA StatiCa Detail and create a new project. Design code will be Eurocode, concrete grade C4050, reinforcement B500B, and the concrete cover according to the project 20 millimeters. I will choose a general input without a template. Using general input, you can import the geometry either from a DXF file through this button, or you can add the entities of beams which can have a specified cross-section. I will choose a T-shape and input the dimensions 130 to the upper flange. Okay, so this will be the cross-section of the middle part of the beam, and its length will be 12 meters. I will model now the hinged parts on both sides. Another beam entity with the length 5.7 meters, and I will turn on the hinge functionality and define the cross-section on the end of the hinge. Only thing I changed was the depth, and I also want to align it to the top edge, like that. I will copy that hinged part and place it to the left side. So let's switch the cross sections and define the master point and insert point of the entities. Now I will input the end parts which have rectangular cross section. The dimension of the cross section will be 600 millimeter depth and 500 millimeter width. And the length of these ending parts is 0.6 meters. And let's align it next to this edge. Master point will be point number 3. Insert point on the new entity, point number 4, like that. Let's copy this to the other part, to the left side. Yes. I need to input supports according to the structural scheme. So I add the new entity, which will be a point support with bearing plate. And let's position it to the ending parts of the beam. The bearing plate will be 0.3 meters, thickness 2 centimeters, and the position will be 0.3 meters from the beginning of the entity. And let's release this support in the X direction, like that. I will copy that to the left part. Master member will be M5 and restrain it in the X direction. Now we have a simply supported single span beam, and the span is 24 meters. Let's input the openings to the middle part by adding new entity. The opening shape will be circular, the diameter 0.9 meters, and the position will be related to this master point number 4 on the member M1. The X position of the first opening will be 1.51 meters and the Z position minus 0.8 meters. And I will copy that opening and have 7 openings in this middle part, all the same geometry, just the X position is always changing. Third one will be 4.44, 5.97, like that. There is also a possibility, of course, to import your geometry from the XF file, but if you want to have a cross-section of the beam, as we have in this example, you have to input them using beam entity, which can have a defined cross-section. Let's take a look at the real 3D view of our beam. This is how the haunch looks like, the openings. It looks all right according to the project. So, with the geometry ready, we can move on to the loads in the navigator. I will want to consider 3 load cases. First load case will be self-weight of the beam. Second load case will be permanent load. And the last one, variable load case. Let's change the type for variable. The first load case, self-weight. I go into the load impulses to fill it with line loads. Let's input a new load entity, a line load with the intensity minus 9.2 kilonewton per meter on the whole length. Of course, in the project, the engineer considered changing line load along the length of this middle part of the beam, and he considered a different intensity of the line load above the openings and in the middle part between the openings. I will choose for this demonstration to show you a constant line load, but you can change the intensity and input smaller parts of the line loads between the openings and above the opening to respect the changing self-weight of the structure. Another line load, now on the hinged part of the beam. The intensity is changing to minus 4.5 because we have a changing cross-section of the beam. Let's copy that to the element M3 here, minus 9.2, like that. And 2 more line loads are missing to the element number M4 and M5. And they will have the intensity minus 7.4 kilonewton per meter. I will copy that to the M5 element. And we have the line load, a simplified line load input here. The second load case, the permanent load, will be also consisting of line loads with the intensity minus 8.2 kilonewton per meter. And I will just copy that to all entities in the project because this line load is constant on the whole length of the beam. The variable load is very similar to the permanent one, just the intensity is lower, minus 5.4 kilonewton per meter. And let's copy that. Like that. Now, for the code checks, we will need combinations according to ultimate limit state and serviceability limit state. I will input 5 combinations in total because we will have 1 ultimate limit state combination, 2 characteristic combinations, and 2 quasi-permanent combinations. Let's change the type according to that. So the second will be characteristic, the third as well. The fourth combination will be quasi-permanent, and the fifth also quasi-permanent. And the rule of the combinations will be according to Eurocode, ultimate limit state 1.15 and 1.15 for the permanent load and 1.5 for variable. For characteristic, we will consider 1, 1, and at first 0, then characteristic 1, 1, and 1 for all the load cases. For the quasi-permanent, similarly 1, 1, and 0, and for the last quasi-permanent 1, 1, and 0.3 as a factor for the combination. Okay. So I will switch off the checkbox for load cases because the code checks will be done only for the combinations. And let's go to the reinforcement. In the input edit of reinforcement, I will show you how to input some groups of bars to the lower and upper edges of the beam. This group of bars will be defined on more edges. You see the edge numbers appearing now, so I will input 2, 3, and 4, and 4. Change the diameter of the rebars to 28 millimeters. Number of bars in a layer can stay 3, according to the design done by the engineer before. We could choose different anchorage types, from simple anchorage up to the perfect bond and continuous bars. And we can also define how the length will look like. Related to the edges, the first and the last edge of the rebar. Okay. Let's input another group of rebars a little above this first group with 25 millimeter diameter, and the concrete cover type will be user value. It will be, for example, 70 millimeters. Let's input another group to the top edge with the diameter 16 millimeters, 4 bars in one layer, and the definition will be on outline or opening edge, and I will choose the top edge of the beam. Let's extend this rebar to the outer edges. Just like that. I will input some stirrups also, groups of stirrups with 10 millimeter diameter, and the entity which we are relating to is M5. This left entity, and distances will be 50 millimeters, and after that every 200 millimeters. Take a look at the real 3D. You see that around the opening the stirrups are cut, but the shape remains correct. And we can check if the designed input rebars fit into our section or not. All right, so of course we would need a lot more reinforcement, especially around the openings, diagonal rebars, also here a horizontal group of bars. So just to save some time, I will click into this fully reinforced model and show you how we reinforced these entities, this model. Here are the horizontal bars around the opening, and we can check it out also in 3D. All right, basically our model is ready. Geometry, loads, reinforcement are all input. All what we have to do now is go to the checks and perform the calculations. I already did that just to reduce the time of the demonstration, and we can go through the results. How are the results looking on the structure, and what are the utilizations of concrete and reinforcement? So right now we are in the summary of all the code checks, and we see immediately if our beam fulfill the code requirements or not for ultimate limit state and serviceability limit state also. We see that the governing item was the strength of reinforcement. In this case, strength of concrete utilization here is 56%, strength of reinforcement we are about 95%. These results compared really well with the design according to the Strat&I method used by the designer, and the differences between the results were 4% at max. Let's go to the detailed result of the strength. At first, the strength of concrete. We see the utilization in front of us, that the utilization in compression was 56%, reached at the top edge. And the utilization for the reinforcement, for the strength of reinforcement was the 95%, and it was reached on the stirrups in the hinged part of the beam. I want to show you the crack width check also, and the other serviceability limit state checks, because those are the checks that you cannot get from Strat&I methods. Using the compatible stress field design, we are able to check where are the cracks forming, their widths, and also we can check the deflection of the structure, which are really important for the engineers in general. Well, it looks like I have a technical issue here. Okay, it just got back again. So we see that the maximum crack width was 0.151 millimeters. The limit crack width was set as 0.3 millimeters. That can be set in the top ribbon. And the maximum width of the cracks was in the hinged parts also. Let's show the deflection. The deformed shape looks like this. The maximal deflection, total deflection was 71 millimeters. This is still far lower than the limit deflection value for this project, so we are on the safe side here as well. We can display short-term, long-term, and total deflections in the application. Another important thing for the engineer can be the bill of material, where they can export the tables of reinforcement with all the rebars that they input into the project, and they can also export it as a DXF file for the drawings. So this was the practical demonstration in the application. Now let's jump back to the presentation and show some of the conclusions of these projects. So for as a last step, we wanted to compare the methods and give you some conclusion. So combining the two approaches, the StratEnTie analogy and the compatible stress field method, enabled the engineer to deliver the design required by this project confidently and according to the valid Eurocode standards. Using this method that I described you in the webinar, the engineer was able to decrease the self-weight of the structure by approximately 15%. So the requirements of the projects were met. And here is a little comparison of the two methods. The StratEnTie analogy provides a safe design, and while it is safe, it can be also really time-consuming because you saw that the engineer had to create several StratEnTie methods to make sure he was designing safely and according to the behavior of the structure. And the results accuracy is also depending on the chosen model. The method is also quite conservative and it cannot check the crack widths or the deflections, which can be also quite important for engineers. The compatible stress field method in detail, on the other hand, provides a quick design and also complete code checks, including cracks and deflections in serviceability limit state. And it also contains a tool which gives you an automatic detection of the ideal reinforced position. That was the topology optimization that was shown in the presentation. And the modifications and the optimization is done really quickly within minutes. You can play around with the size of the openings, the alignment of the rebars as well. So, are there any questions, Honza?
Thank you, Yoshi. Yes, there are questions. One of the question is where we can calculate the topology optimization. Can you please show us in the application where's the option to calculate the topology optimization?
Thank you. So I will go for the first model that I created from scratch. And in the reinforcement part, we have design tools. We, in fact, have two design tools. One is the linear analysis, and one is the topology optimization. The topology optimization is the more advanced one. It uses an iterational process, and with this, it shows you the areas in compression and in tension in the structure, so you can decide where to put your reinforcement to achieve the most optimal layout.
Okay, so maybe it will take some time to calculate it. Maybe in a while. There's another question. One user asked if it's possible to design a pre-stressed beam in IDEA StatiCa Detail.
Well, now we don't have the entity of a tendon, of an actual tendon in the input entities of a project, but you can design such a structure using equivalent load effects. So instead of inputting a tendon, you could input the equivalent load into the load cases and replace the pre-stressing effects with that. Another approach would be to import the complete beam or just a part of the beam from IDEA StatiCa beam, where I will show you this beam application, what I meant. We have a direct link with this application, and you can import it, including all the load effects and combinations into IDEA StatiCa Detail. Another approach would be if you have a curved tendon, you would like to input the load effects of the pre-stressing onto a polyline or a spline maybe. So now in the version 10.1, we have the option for the line loads to be input on a polyline from DXF reference. You can import the line, which can be a polyline or a spline from DXF. The definition should be set as a polyline. and then the button for the DXF import appears, and we can import it and place it on wherever we want on the beam.
Okay, thank you for your answer. I'll maybe add one more to IDEA StatiCa beam. There are maybe some people who don't know this application well, but you can go to our resources at web, and we have tutorials for RCS and beam, and you can see pre-stressed double pitch beam here, step by step. It's precast member. So if you go through this one, you can see all the construction stages here, and after designing everything, you can just export this member to IDEA StatiCa Detail, apply openings, etc., and co-check it. So this is the maybe quicker way. And also you can go to this webinar. If you go to webinars, we have all the webinars, and I will show you this one, which may be a little bit interesting for you. It's a beam design and coaching of beams created in SCIA Engineer. There is a shown workflow between SCIA Engineer, which can be applied for any other FEA software, and then IDEA StatiCa beam, and then Detail. Yeah, so you can see this webinar, which will give you more detailed answer for this. So this is about the questions. So now I think our time is running out, so the rest we will answer individually. So after the webinar, I would like to ask you to fill our short survey. We are happy for any comments. Give us any suggestions what you want to see in another webinar. If you have any feedback, give it to us, please. And if you want to get a trial version, you can do it at our web, free trial button here. And as I shown you, go to the resources and webinars for more detailed information. We have also planned next webinars. The first is on 13th of November, steel webinar, which is focused on correct models, how to build it. And the next concrete webinar will be on 27th of November, which will focus on continuous composite bridge. So join us for the next webinars. And this is all for now. We thank you for attending the webinar. If you have any questions, just fill it into survey or write an email to us or to your resellers. So thank you very much for watching us.
Thank you. Goodbye.
Bye.